Welcome to Plutus IES, and today we are trying to explain how we can define the stability of coordinate compounds. Now, whenever we talk about stability of the coordination complexes, we need to take into account two important things. The first one that comes is that what type of stability are we talking about? Now, based on this we can classify that there are two different types of stability. Number one, the first one is called as your thermodynamic stability. Thermodynamic stability, whereas the second one is called as your kinetic stability. Kinetic stability. Thermodynamic stability comes from thermodynamical parameters like change in the Gibbs free energy, lowering enthalpy change to negative, increased in entropy. This we mostly case when we encounter when we have chelating ligands. Chelating ligands also, it can also be explained on the basis of CFSE. Now, for the case of CFSE, we already know that the CFSE of square planar complexes is always the most highest. That means thermodynamically square planar complexes are the most stable complex to be formed. Then it is the octahedral complex, and then at the very end we have the tetrahedral complex, which have the lowest of the symmetry and hence will be the least stable thermodynamically. Whereas kinetic stability comes from, kinetic stability refers for how fast the rate of substitution of a ligand can occur, whether a given complex can undertake part into substitution reactions or not. Since all the ligands behave as nucleophiles, we can say that kinetic stability mostly refers to your nucleophilic substitution reaction. Nucleophilic substitution reaction, at what rate it is occurring. So let's move forward and let's try to explain these different types of stabilities. So first we have thermodynamic stability. Thermodynamic stability. Now the thermodynamic stability comes from the interaction of metal and ligands. It comes from the interactions of metals and ligands to form a coordination complex. So based on that, the factors that are responsible are the properties of the metal, which will help us to explain whether a given interaction between the metal and ligand will lead us to a stabilized complex or not. Now, for the case of ligand, we mostly take into account basicity. If your ligand is very much basic, we'll call it a very good ligand. If not, we'll call it not. The higher the better the interaction between the metal and the ligand, that will decide that whether the given complex is thermodynamically stable or not. So for the purpose of metal, the first thing, it depends on what is the geometry that the metal is taking. Based on the geometry, we have already classified that the complex will be, if they are square planar, they will be the most stabilized, then it is the octahedral, and then it is the tetrahedral, which will be the least stable. Then it comes to the oxidation state of metals. Now, since ligands are acting as nucleophile, that means metal should act like acids or Lewis acids. So that means higher oxidation state higher oxidation state promotes better metal ligand complex, hence it will increase the stability of the complex. But what if the complex that I'm taking, they have exactly same oxidation state? Then what I can decide? When you encounter a complex having the same oxidation state, we can move to the size. Now, because oxidation state refers to the charge on a metal center. Now, if the charge is present over a very large sized cation, that means the charge density is very much low. And when the charge density is very low, that means the ligand will have a hard time to approach the metal center. So when size decrease, that means the charge density will increase, the metal to ligand interaction will increase, and the complex will be more stable. Now, based on this, I can also explain that for higher oxidation, if I need to talk about that, aluminium whole thrice, aluminium H2O whole 6, 3 plus complex will be more stable as compared to magnesium H2O whole 6 complex. And this we can use to define the stability between the complexes. Now, when it comes to size, for example, if I have magnesium complexes whole 6 with charge 2 plus, comparing it with a calcium complex with exact same charge. So if here we can see that from magnesium to the calcium, which is down the periodic table, we can see that the size of calcium ion is increasing. Now, when the size of calcium ion is increasing, that means charge per unit area is decreasing. So that means here the magnesium complex will be more stable compared to calcium H2O whole 6 complex. After oxidation, the next thing we encounter is the effect of chelating ligands. Chelating ligands. For chelating ligands, we can explain as, for example, if you have a metal complex of some charge Mn, and let's make it an entire complex. If I have a complex of some MLX type ligands, let's take a different example of metal, ammonia, whole 6, 3 plus complex. And I'm trying to replace it with ethylene diamine ligands. So when the reaction occurs, we'll have some complex like this with remove 6 ammonia ligands. Here you can see that I have one metal ion complex, 3 ligands, total 4 ions are on right hand side. Here there are total of 7 ions on the product side. So clearly, going from left to the right side of the reaction, the entropy of the system is increasing. Now, since we know that the Gibbs free energy can be represented as delta H minus T delta S, since the entropy is increasing, that means the overall negative value of T delta S will increase, which will facilitate the negative Gibbs free energy. Hence, the formation of the complex will get stabilized under thermodynamic parameters. That's why chelating ligands always form the most stable complex for any metal complex we know. Now, the last property that we can use to explain is your HSAB principle. HSAB principle. HSAB principle, what does it state? The HSAB principle states, also goes by the name of hard acid, hard, soft, acid base concept. Acid base concept. Here it states a hard electronic center will interact with another hard electronic center, a soft electronic center will interact with another soft electronic center. In such kind of scenarios, the bond that is occurring between a hard and soft electronic centers, the bonds will be very much stabilized. But any other combination, that means hard soft or soft to hard, the bond formation are not that stabilized and the bond will be weaker. So first we have, since we are talking about metals, we'll be talking about hard acids because they are electron deficient. Hard acids are your metal centers that have large size, that means they should they have large charge. That means their higher oxidation should be very much stable, and then they should have the small size. Based on this, we can say that whatever the complex they will form, they will be highly stable. Then we have soft acids. Soft acids are the one which have opposite properties of the hard acid, like they have small charge and they have large size. The prior example of soft acids are from your scandium to chromium, while for the hard acids, the most stable complex will form from cobalt to zinc. Okay, so these were the properties that are responsible for stability of complex that contributes towards that comes from the metal. Now, for the ligand, the stability mostly comes from the basicity, and we already know basicity depends on which factors. Basicity depends on, number one, basicity depends on electron donating groups, which increases the basicity. For example, if I need to mark pyridine is less basic compared to meta substituted pyridine, which is in turn is less basic compared to para substituted pyridine. Then we have steric hindrance. Steric hindrance. What does steric hindrance do? Steric hindrance poses a restriction between the interaction of metal and ligands. If the ligand contains too much of bulky groups, the metal and the ligand cannot properly interact with the metal. Hence, the steric hindrance decreases the basicity of the complex. And when basicity decreases, that means the stability of the complex will dwindle. The most primary example we have for this is the case of, let's take pyridine and ortho-substituted pyridine. Now, this alkyl group, which is at the ortho position, when this lone pair are trying to interact with the metal, these bulky group interfere with the ability of the pyridine molecule to come closer to the metal center, and because of which it has a lower basicity compared to pyridine. Hence, this is a much better ligand compared to this case. Hence, the complex formed by pyridine will be more stable compared to ortho substituted pyridine. Okay, so I hope this would have cleared all your doubts regarding the stability of the complex, which are the factors that affect them, how we can decide the stability of the complex. In case of any doubts, you can add it to the comment section or any new topic that you want us to discuss. And that's all for my side for today. Thank you for joining us.